factor times y minus b plus the remainder term of x minus a y minus b, and it is the approximation term. Once x and y approaching a and b, this remainder should equal to 0. So it is exactly the same equation as you can see. Okay? So it's supposed to be the same equation. So once more, the equation of the tangent, it's gonna be very, very simple. As I told you, this is mainly the remainder term. Once it can be decayed, as you can see, around the once x and y approaching a and b, as I told you. Okay, differentiability in R2. That's the tangent plan equation can be easily got from this equation. This is the value of the function at a and b, and those are the multiplication of partial f partial x, partial f partial y times x minus a and y minus b, and that's the tangent equation that we are using in order to approximate the values, as I told you. Once more, differentiability in R2. Consequence of differentiability. If f is differentiable at AB, f has both finite partial derivatives at AB. And also, if differentiable at AB, f is continuous at AB. So the 2 points are with us. Once more, if consequences of differentiability. F is differentiable at AB, f has finite partial derivatives. F is differentiable at AB, f is continuous at AB. But the existence of finite partial derivatives at the point, remark, it is a necessary condition for the function to be differentiable, but it's not sufficient condition for the function to be differentiable at that point. And these two statements are really very important. It can come to you in multiple questions, or state right or false, or choose the right answer. It can be handled this way. Okay, in R2 in general, this is the definition of the function when it's gonna be differentiable, and it's exactly like the definition in R, just only with the slight difference. In R, we are dealing with just only x minus a, but here, since we are in the 2 dimension, this is the general definition. And also can be generalized for 1n. To prove that a function is differentiable in R2, we must do the following. So we saw how to prove that the function is differentiable in one variable. Okay, in 2 variables, what are we going to do? Step number 1, find partial derivatives. Okay. Either by using the laws, the principal laws or the definition, or getting the partial derivatives directly. It's really up to you. And it will also be a consequence on the function given. If the function is piecewise, I will have to use the definition. If the function is just only one function defined on the whole domain, I can find f sub x and then f sub y. The second step, so remark, before we go to the second step, if not exist, if the derivatives, partial derivatives don't exist, then the function is not differentiable at this point. خلاص, you are stopped. It is differentiable. Find the expression of r of x minus a, y minus b. If you remark, Omar, in order to get the definition of r of x minus a, y minus b, I will move those terms to the other side. That's the definition of r, as we will see. Step number 3, check whether the limit tends to 0 or not. Remark, if the limit doesn't exist, if this limit doesn't exist, or if it is approaching any other value than 0, then the function is not differentiable. So once more, how many steps? 3 steps. The first step is to find the partial derivatives. The second step is to find the expression of r of x minus a, y minus b. From where are you going to get that definition? From this step. So r is equal to take those 3 terms to the other side. ماشي؟ يعني take once more يا عمر, I can write thus r of x minus a, y minus b equal to f of x, y minus this guy f of a and b minus that one partial f partial x, or simply I can write f sub x, okay, f sub x, okay, at the point a and b times x minus a minus f sub y of A and B times Y minus B. So all I did is I've taken all of these three terms and moved them to the other direction. This is what I did. Okay, that's how to evaluate the value of R. Once you evaluated the value of R, already you have the value of R with you, I can continue. Once I have the value of R, then I will check the limit. This limit is equal to 0. I will give you more than one example, and I believe you have a lot of examples in this PDF. I've already sent it, as I told you previously. He's asking you to check using the definition. Here he's asking you, requesting to use the definition. So I can't solve it directly. You will have to use the definition. Okay, whether the following function is differentiable at 0, 0 or not. So I will do the 3 steps. Okay, the first step, find the derivatives of f at 0, 0. In this case, I will use the definition of partial derivative at this point. I will have the partial derivative in the direction of x, which is simply f of 0 plus h minus 0 minus f at 0, 0 over h. Omar, it's really very simple. What I am doing is exactly, I'm finding f dash at 0, which is the limit of h tends to 0, which is simply f of 0 plus h minus f at 0 over h. This is the in one direction law. But if I am in two directions, Mr. Omar, the law will be f dash at 0, 0 equal to limit h tends to 0. In this case, I'm getting the x direction, the derivative in the x direction. So it's going to be, Mr. Omar, f. I will change only the x component, so it's 0 plus h. The y component remains the same, minus f at 0, 0, and then divided by h. If I want to find f sub y at 0 and 0, it's going to be a limit of h tends to 0. Simply like the value of the function x is 0, but the y component is 0 plus h minus f at 0 and 0 and divided by h. These are the two main laws that we can use in order to find the partial derivatives of your function as you will see. So, once more, okay, this is partial f partial x. It's going to be limit 1 plus h minus 0 minus f at 0 over h, which is going to be, once you start to substitute, it's going to be 0 plus h to the power of 2 plus 0, which is going to be h squared, minus 0, because the definition of the function once y is equal to 0 is 0. So it's going to be h squared, it's going to be, once you start replacing, it's going to be h squared minus 0 over h, limit h tends to 0, which is going to be h squared over h, limit h tends to 0, which is going to be h, limit h tends to 0, which is going to be 0. This is the result that you can see. Okay? Simply like for the partial derivative with respect to y. With respect to y, it's going to be, if you remark, here the x, I will change it because I'm in the direction of x. Now I'm getting the direction of y, so this is the y component to change it. Once more, h tends to 0 will make this function come to h squared minus 1 over h, which is just only h, take the limit of h tends to 0, the result will be equal to 0. Now I have the first derivative, partial derivatives at the origin. The second, I will need to find the definition of r of x minus a, y minus b. But remark here, a and b are zeros. So all I have to do is to write f of xy. Once more, I can write it this way. F, Omar, I'm writing and I'm showing you on the slides because I need more concentration, and I know I want these equations to be as easy in digestion for you as much as possible, okay? So once more, f of x and y is going to equal to the value of the function at 0 and 0, then plus f sub x at the origin times x minus 0, then plus f of y at the origin times y minus 0, all of this plus the r of x minus 0, y minus 0. If you remark, the value of the function at the origin is given by 0. So this guy is equal to 0. F dash, I have it equal to 0, and f dash y is equal to 0. So this is 0, that's also 0. Which means r of x and y is equal to the value of the function of x and y. And the value of x of function is x squared plus y squared. Now I have the function of r, x, and y. The third step, so the second step is already done. The third step is to find the limit. Can you remember the limit?
Yes.
Limit of x and y tends to 0 and 0 for r of x and y divided by the magnitude of x and y. Once you start substituting, you will have limit x, y tends to 0 and 0. For this guy, it's x squared plus y squared. The magnitude of xy, it is the square root of x squared plus y squared, which means it is root of x squared y squared, taking the limit of x and y tends to the origin, the result is equal to 0. Once this limit is equal to 0, then your function is differentiable. So, once more, let's repeat all of this. So, the third step, this is the third step. F of xy equal the value of the function. Because the first derivative times x, the first derivative of y times y, plus the remainder term. Remark. This guy is equal to 0. That guy is equal to 0. And the f of 0 and 0, so the value is given by 0. So, the first term, second term, and the third term are all zeros. Which means r of xy is equal to f of xy. Now I can do the third check, which is limit xy when r of xy divided by x squared by the magnitude of xy. Just making the substitution using this guy, using this relation, you will find the root of x squared plus y squared, which is equal to 0, which means your function is differentiable at the origin. Same steps and everything, I will redo it once more, but with another problem. Look to this problem. I need to find, also using the definition whether the following function is differentiable at the origin or not, and he is giving you the root of xy for xy greater than or equal to 0 and for xy less than 0. By the idea, xy is greater than 0, which means in the first and third quarter. Xy less than 0, it means in the second and the fourth quarters. Okay? These are the value of the function, as you can see. So, first step, I will try to find the derivatives of f at 0 and 0. I can do it using the law. Or also I can do it using the general equation of the derivative. Okay? But in this case, since I'm separating the domain of xy or R2 into first and third quartils, second and fourth quartils, I will have to use the definition. The definition states that limit 0 plus h minus f0 0 over h, and once you start substituting, it will be the root of 0 times 0, which is 0, minus 0 plus h times 0, which is also 0. So the denominator is 0 before even using the limit. It's already existent, equal to 0. If I want to find the derivative in y, it will be exactly the same. So once more, the second step is to write the expression of the limit, which is, once more, that's your f function. If I try to substitute the value of the function at the origin, it is equal to 0. Partial f partial x is equal to 0. Partial f partial y is equal to 0. The only thing remaining is r of xy, which equal to the main function. So now I can find the limit, as you can see. That's the limit of r of x and y. In this case, I will replace the limit, r of xy by the root of x, y. and this guy by the root of x squared plus y squared, as you can see. But remark, I can do this limit, directional limit, okay? Because it's a limit in R2, as we did previously. So I will check at y equal x. When y is equal to x, this means this guy will be x squared plus x squared, as you can see, which is gonna be root, and this also will be x. So it's gonna be root of an x squared divided by the root of 2x squared. That's the value that you can see. Okay? In this case, the limit exists. The limit exists, but it's not equal to 0. And so the function is not differential. If you remark at the beginning of this part, in studying in R2, we discussed that we can find, first of all, we will have to find the partial derivatives. The second step is to find the definition of R of xy. The third step is to evaluate the limit. But once you evaluate the limit, it has to be equal to 0. If it doesn't exist, or it is not equal to 0, then your function is not differential, as you can see. So in the previous example, it was differentiable. In this example, it is not differentiable since the limit doesn't equal to the origin, as you can see. Here, differentiability in R2, similar problem with the same list. He wants you to check f of xy, which is x over y. That's the problem. If you remember, we solved one like this previously. X over y, where a is 1 and 1 and b is 1.1 and 0.9. He wants you to approximate the value of the function at b. So first, I will need to find the derivatives. Second, I will use the relation in order to approximate. So once more, find the partial derivatives. The partial derivatives, I don't have to use the definition because I have now f of x, which is x, بص كده, f of x and y, which is x times y to the power of -1. So f sub x is going to be y to the power of -1, which is y over 1. F sub y, I will differentiate the y part, which is going to be negative x times 1 to the power of -2. That's negative x over y to the power of 2. Okay? That's f sub y. So the first step is at 1 and 1, I will get f differentiated with respect to x, which is going to be 1 over 9. F differentiated with respect to y, which is going to be negative x over y squared. I will make substitution. So f at 1 and 1, I f xy at 1 and 1, all I have to do is to substitute 1 over 1, so it's 1. And then f of y, the first partial derivative in y, what was respect to at the point 1 and 1, it will be negative 1 over 1, and so the result is negative 1, as you can see. Now I have the value of the function, okay, and then also I have also f at 1 and 1 is equal to positive 1. I have the value of the function, I have the value of the partial derivatives, I can write r of x minus a. So now, if I want to write the equation, once more, I've wrote it in order to have it in front of you. It's going to be f dash times x minus a, f dash times y minus b. And that's the value of r of x minus 1, 1 minus 1. That's after defining and finding the value of f. طبعا f is equal to 1, as I told you. I'm sorry, this is equal to 1. And for the first derivative, it's 1 times h. And the other one is times k. This is the limit that I'm using. That's limit of h indicated to the origin. F of 1 plus h, 1 plus k, minus f 1 and 1. The first derivative times h, the first derivative times k, and it is divided by h squared plus k squared. All I have to do now is to simplify the denominator. So I'm using just the value of f of 1 plus h, 1 plus k, which is going to be the value of my function, which is instead of x will be 1 plus h, 1 plus k, and then the value at 1 and 1, the first partial derivatives, and that's going to be the kernel after we substitute. الكernel ده جه منين؟ الفاليو دي جت منين؟ الفاليو اللي احنا شايفينه قدامنا, this is the value of the function at h and k. In details, I put it in this style. بص كده. تعالوا معايا step by step. This is the value of R, which is F1 plus H, 1 plus K, minus F11, minus F of X at 1 times H, and the first derivative, partial derivative in the direction of Y, times K, and all of them divided by the square root. This is a simplification of the function. If you simplify the denominator, it's going to be negative K, H minus K over 1 plus K. Times the root of H squared plus K squared. That's the denominator of how we evaluate R. Okay? Once more, I will start to prove, or how to prove that this limit exists and is equal to 0. This is very, very simple. I can use the general definition of Cauchy that we did go through. Before I go further, I don't know. Do you know how we get R to be after simplification on this form? Or how it is going to be on this form? It's very, very simple. All I have to do is to make substitutions. That's the value of R. So I need the function at 1 plus H, 1 plus K. Let's do it. 1 plus H over 1 plus K. Then minus if at 1 and 1, if at 1 and 1 is equal to 1. Here we go. Then minus the first partial derivative at 1, which is equal to positive 1, times H, that's H. Then plus the value of the function at Y, which is equal to negative 1, times K, which is negative K. I need to simplify this. In order to simplify this value, بص يا عمر، مفيش حاجة اسمها أنا هكسر أو هرجع عن شو. In order to differentiate or to simplify, I will have a common denominator, which is 1 plus K. The first term is 1 plus H. The second is minus 1 plus K. The other one is going to be negative of an H plus K times 1 plus K. Then I will try to simplify. Once you try to simplify these values, you will have 1 plus H minus 1 minus K, then minus H, 1 times H, which is H, then minus over K, then this is H, this is plus HK, then you will have negative K, then plus K squared. And all of this is divided by 1 plus K, as you can see. Remark that positive H was negative H. You will have H and K, and it will be simplified, and then you will reach this relation. Okay? It will be negative KH minus K squared over 1 plus K, which is simply can be what of this one. This after simplification. So all I have to do is just to make substitution, and this is why I'm telling you it's really very important. Once you start these problems, is to use your pen and paper and to try to solve them, because the details that being digested with the steps. So just trying to make this substitution will leave you with this value. That's the denominator. I will divide it by the root of H squared plus K squared. Now I want to evaluate the value of this function, which is K and H minus K. Of course, I'm in the 2 dimension, which is divided by 1 plus K, and this is the square root of H squared plus K squared. According to our theories and what we did go through previously, this is going to be less than or equal to the absolute of K times the absolute of H plus the absolute of K divided by 1 plus K times the root of H squared plus X squared. Once more, it is less than or equal the absolute of K. Okay? I can replace H according to the relations that I've told you about, which is can be replaced by the root of H squared plus K squared plus, same way like I will replace k by the root of h squared plus k squared, and all of this is divided by 1 plus k times the root of h squared plus k squared. If you take these two guys together, it will be let them equal absolute over k times 2 times the root of h squared plus k squared divided by the root of h squared plus k squared times 1 plus k. Those two guys will eat each other, and you will end up having absolute k times 2 divided by 1 plus k. If you take the limit of h and the k tends to the origin, this value is going to equal to 0, which means you will remember is equal to 0. It means that the function is differentiable, and I've proved all this. Once it is differentiable, now I can use the relation of the tangent plan. This is, as I told you, how to prove that this value tends to 0, and so the remainder is tending to 0 further than the magnitude of x and y, so the function is differentiable at 1 and 1, and in this case I can use the approximation.
Okay.
What's the approximation? Because he wants you to evaluate near point 1 and 1, the value of the function. Like, is there an approximation? The approximation tell you once more, f of x and y equal to f at 1 and 1 plus f sub x 1 and 1 times x minus 1 plus f sub y at 1 and 1 times y minus 1. That's the main equation of the tangent plan that I will use to approximate. So once more, everything that I told you about, here we go. Those are the main terms. The value of the function at 1 and 1. The value of the function at 1 and 1. The first derivative with respect to x. The first derivative with respect to y. Substitution in all of them. Now I have the derivatives. I've wrote the equation that I just wrote to you. F at 1 and 1, f of x at 1 and 1. If y, making the substitution, that's the equation. Okay, I need to evaluate it at 1 and point 1 and point 9. What I have to do is to replace every x and y by these two values, 1 and 1 and point 9. Then I will have the approximated value. This problem is really very important. It did go through, if you remark, Omar, it's an integrated knowledge of all what we did studied previously, starting from the going through the limits in 2 dimensions, going through the differentiability definition, going through the equation of the tangent plan, how to use the approximation, how to formulate the limit. So it's really a very good problem. Okay? Here also he wants you another problem on all of this. He wants you to find the equation of the tangent plan to a graph of f. In this time it is then 2x plus y. So the function, my function is len 2x plus y, and he wants you to make the approximation, okay, of the tangent plan at the point -1 and 3. Exactly like we did previously. Try to get the first derivative with respect to x. So I'm differentiating this guy with respect to x. It's going to be 1 over 2x plus y times 2. Finding the derivative with respect to y, 1 by 2x plus y times 1. Here is the partial derivative with respect to x. That's the partial derivative with respect to y. Substituting in each one of them by the point that I need -1 and 3. Can you write my equation? The equation is going to be f of xy equal the value of the function at -1 and 3. But then the first derivative at -1 and 3 times x plus 1. Then the first derivative times y minus 3. Here we go. That's the equation that we are using. So all I'm doing is just making the substitution. That's the value of the function at -1 and 3. So بص كده يا عمر، نعمل substitution ب -1 and 3. This is going to be -2 plus 3. So the result is 1. So it's again 1, which is C. Then 2. If the derivative with respect to x is 2. The derivative with respect to y, which is 1. Here we go. This is x plus 1, and that's y minus 3, as you can see. Okay, and that's the definition of the derivatives. It's equal to 2x plus y minus 1, the value of the approximation. If you need to find the value at negative 1 and 3, all I have to do is to substitute by the point near negative 1 and 3. I want you to stop and for a second the relation between the existence of partial derivatives and the differentiability of the function. Okay? So once more, the existence of partial derivative at the point is a necessary condition, not a sufficient condition. It's just a necessary condition for conversion to be differentiable at that point. But it's not sufficient condition as I told you. Okay, it is possible to find the partial derivative of a function at a certain point, and that function is not differentiable at this point mainly. So you can find your partial derivatives, although your function is not differentiable. I believe you have here a couple of examples on these issues. This is also one of the problems that you will find in your list number 2. They want you to define the differentiability domain of the functions, defined it by the following expressions. I will solve the first one because it's a little bit complicated. So all I have to do is to follow the steps. The function is a quotient of polynomials, so the polynomials have no problem, but the only problem is when the origin, because it's not going to be defined, but also, as you can see, I've extended the continuity of this function, as I have gave you when xy equal the origin, take the value of the function is equal to 0. So it's extended to continuity by this condition. So it is differentiable on R2 except at the origin. The only potential problem at the origin, this is, we check the differentiability at the origin. In order to do this, all I have to do is to get the limit of xy near the origin for x squared y plus y squared x over x squared y squared. Before we go further, if you remember, I will use the directed method. We will use the directed method. In the directed method, I will replace each y by mx. So it's going to be x squared times m squared x squared times m squared x squared times x, and that's the result as you can see. Okay? Once more, I can take x cubed as a common, which is going to be eliminated by x squared, and this is the result. So once the limit x tends to 0, the value is going to be 0. Also, I can check for another curve when y is equal to x squared. So I will make the substitution, replacing every y by x squared. So it's going to be x squared times x squared, and then you will have x to the power of 6, same way like, and make the substitution also will tend to 0, as you can see. So either in y equal to m of x or y equal to x squared, the result of the limit is equal to 0, which means the function is differentiable. Okay, partial derivatives at the origin. Okay, I will make f of h at 0 minus f of 0 over h, which is going to be if h at 0, start putting the x's equal to 0, and then this value will be equal to 0 directly, which is equal to 0. The gradient vector is zeros, so now I have the gradient vector, which means the first derivative in the direction of x and in the direction of y are both of them are equal to zeros. So the value of the function will equal to the remainder term. This is why I wrote r is equal to r of f is equal to f of xy minus the value of the function minus the gradient vector times xy. So the remainder term is just only the function which is x and y. This is why f of xy divided by x squared plus y squared. If I make the substitution of this relation, the limit will tend to 1 over root 2. Since it is not equal to 0, then the function is not differentiable. So remark Omar, also the partial derivatives here and there exist and equal to 0, but the limit of the remainder term is not equal to 0, and so the function is not differentiable. Okay? That proves the differentiability. So the domain for this one is going to be R2 except 0, as you can see. All the concept of Rn can be applied exactly for n dimension. So I'm just extending the definition. If you remember, instead of having x, y, f of ab, partial partial f partial x partial f partial y times x minus a y minus b, and the remainder term. This is the extension. If I'm talking about n dimension, it's exactly the same as you can see. This question is very nice. He wants you to state if the following propositions true or false. Let r squared into r be a function such that partial f partial x is equal to 0, partial f partial y is equal to 1. And he asks you if the partial derivatives at the origin, at 0, 0, are different, we conclude that f is not differentiable at the origin. Of course, it's false, because there is no relation between the values of the partial derivatives if they are the same or different with the differentiability. So the answer is false. The second part that I want to talk with you is some past papers exercises that exist. I've already sent you this bunch of slides, and that's some examples on how to be asked about this one. Like this example for like this problem, he's giving you 50 points. Consider the function r2 into r, that's the function given. Define d, define the continuity of f, the extension of the function. All of these questions we already taken in the previous part. Compute the existence or initiate the existence of the gradient factor. That's another problem also. He wants you to select the correct option of multiple choice, and this was in calculus, the midterm 1, in calculus 23-24. This is another problem with a vector valued function where he wants you to define and graphically represent t. This is like the problems that we had previously. Find the range of f of t, geometrically represent the level curves of f3 when e is equal to 3, if you remember. Okay? In this one, the function is defined by e to the power of xy and then negative 1 when x times y is equal to 0. He wants you to characterize f dash to start stating the domain and codomain, and also find f dash at 0, 1 and the f dash at negative pi plus 0 for these values. That's another function exactly like what we have been taking, and he wants you to show that the limit of this function